Thanks. So as Daniel said, yeah, I'm going to talk some about GPU programming, but I think the way I'm going to go about it is I'm going to kind of just run through the graphics pipeline, kind of what it is, graphics hardware. I'm going to go through this pretty quick because I have a feeling most people here have at least some familiarity with it. Some, I can tell, have a great deal more probably than even I may at this point. Then I'm going to talk a little about the graphics APIs, which is how you've traditionally at least gotten at this hardware. And then I'm going to talk a little towards the end about ATI's new sort of initiative to be able to access this functionality more effectively for computation. Okay, so just to be clear, I try to sort of be clear what I'm talking about before I start talking about something. So when I talk about graphics hardware, I'm talking about this stuff in the blue box. All right, and so and this is sort of the X1000 series, where I write X1K from ATI. Okay, those of you who are familiar with these things, these are the X1600s, 1800s, 1900s, these sorts of things. But don't worry about that. So this is how the graphics hardware sits in your PC, sits in your system. Okay, it talks to this memory controller for the CPU called the North Bridge through this PCI Express 16X bus. Inside this thing, there's a host interface. There's a 3D pipeline and a memory controller that goes out to graphics memory, which is on the card. And this is a quite a wide bus, 256-bit bus. Okay. Now I'm going to stick to the 3D pipeline and to some degree the memory controller. There's other important graphics stuff in here I'm not going to talk about, things like 2D blitters, MPEG decoders, or things that support MPEG decoding. Gosh, I'm forgetting other important things too. But since this isn't where I spend my time, it's over there. I guess it's not surprising. But there's some stuff I'm leaving out. Just realize that. Okay, so the 3D pipeline, this kind of just comes out of a graphics textbook, I suppose, in some ways. There's a command processor up at the top. It sends data to this vertex processor, which does processing sort of on geometry. Then that data is bundled up into what we call primitives. Those things would be triangles or line segments or points. They get rasterized, which means the pixels corresponding to them get spit out. But I'd like to distinguish between pixels, which I think of as stored in the frame buffer, and fragments, which haven't gotten to the frame buffer yet. So we call those fragments instead of pixels. Those fragments get processed to find out what color they should be when they get in the frame buffer. And this is where a great deal of the computation ends up happening. Then there are some per pixel operations to incorporate those fragments into the frame buffer, and finally things go to the frame buffer. Okay, we're at the point now where the speeds of these things have gotten quite high. You can do 1.2 billion vertices per second. Okay, so think if you're rendering every 30th of a second, I mean that's many, many millions of triangles, because each vertex can define a new triangle using the last two vertices and the current ones. That's why the number of vertices gives you as Kurt Akeley used to say, the not to be exceeded rate for the maximum number of triangles you can draw. And then we're at the 11 billion pixels per second, okay, is the rate we're at. Now actually getting these numbers, of course, is a different matter. But if you think about what, this can allow you to draw the screen, 1,000 by 1,000 screen, that's what, 1 million pixels? I mean, you can run, even at a 30th of a second, you can draw that over many times in one frame these days. Okay, so there's a lot of stuff you can do. Okay, we now have these programmable vertex and fragment processors, and they allow, beyond allowing sophisticated shading and getting really pictures on the screen, there's sort of more stuff that you can do now than you used to be able to. So you can have this high depth complexity that has to do with being able to draw the screen many times over itself. You can do these multi-pass algorithms where you draw things multiple times. We also have floating point frame buffers, so you can do things like high dynamic range. I'll show a couple examples of this, and anti-aliasing. Okay, and then also now we finally get to you can because of the programmability and all this sort of high speed, it starts becoming interesting to do computation on GPUs that has nothing to do with graphics potentially. Okay, so let me just talk very at the high level of ATI's current hardware. So there's 8 vertex engines and 16 fragment engines, okay? And again, right, these are the vertex engines go up in the vertex processor, the fragment engines go in the fragment processor here, okay? They do these sort of 3-component vector plus scalar, so sort of a 4-component multiply add on every cycle, IEEE 32-bit, almost IEEE anyway. I see we have a few, okay. Few troublemakers in the audience. And on this 1900 series, we actually have sort of 3 ALUs per per fragment engine. So there's 48 of these ALU cores that can do these 4 by 32-bit things on every cycle. We do dynamic flow control in the programs, okay? By dynamic, I mean you can do if some condition computed by the program, then and else, as opposed to if some static condition that never changes, then else, which is kind of boring, okay? But so now we can do dynamic flow control. We have these fairly large memory configurations. This is the amount of memory on the board. These things run at about 650 megahertz for the processors, 775 megahertz for the memory. Remember, and this is running a 256-bit bus back and forth to the chip. Okay. All right. So I'm going to run through this pipeline. I'm going to try and go pretty quick, just to talk about what the different pieces are. So the first thing is there's the command processor is at the top, and one of its responsibilities is to control the rest of the pipeline. So the only question here is whether that control takes effect immediately when you send the command, or whether it gets pipelined, meaning it goes in behind anything else that's already in the pipe. This is a deep pipeline, okay? And so you may have already switched to the next scene, but the back end of your pipe may not have yet. And so if you send a control signal down to the per pixel operation saying, change the blending function to be blending function 12 now, you're probably saying that too early, right? Because stuff hasn't drained through. So there's this question on control about whether it actually just goes through like the rest of the stuff through the pipeline, or whether it happens immediately. That's the only real issue there is there with that. And some kinds of control are so complicated that you can't really pipeline it through, and so you have to do this, and you have to wait for the pipe to drain before you can do it. Okay, so now we come to actually processing some data. There's kind of 3 ways to get the vertex data that define the geometry you're going to process. Okay, the most straightforward way is for the CPU to just send them. Okay, this is the old immediate mode. Okay, and the CPUs to send stuff. These days, if you have a lot of data, that might be kind of slow. Another thing you can do is store the data in graphics memory, and then the CPU just sends indices to say which vertex it's supposed to be. Okay, and then finally, the third way, this also sort of corresponds to the way history kind of went in doing this stuff, is to store both the indices and the vertices on the graphics card, and have the CPU just send a command that says start. Okay, so these are the 3 ways to get a hold of vertices. All right, and they depend on sort of where you're storing them. Okay, then comes the actual vertex processing. And so when you have these vertices, what do you do with them? There's obvious stuff that has to be done. You have to transform them so that they're in the right orientation for you to be looking at them. You have to do the perspective effect. There's a bunch of other stuff. Okay, so. This is sort of a forward reference. They look a lot like these fragment processors, which I'll come to again. They have these 4-component dot product engines. You do 4 clocks per vertex per engine, so this is how we end up with that rate I showed on the first slide of 1.2 billion vertices per second, that in the 650 megahertz rate. Okay, these things are on 32-bit floating point. They have these things, these arithmetic instructions like multiply, add, 1 over x instruction, 1 over square root of x. You can do comparisons or set on less than, those sorts of things. And then you can use those comparisons in flow control instructions. So you can do both calls and returns and looping and so forth, but you can also make them conditional. Okay. Then once you're done processing the vertices, there's some final steps that have to happen. These are typically hard-coded. Well, there's usually a combination of hard coding and programming. So I'm not going to spend much time on these. These are sort of, this clipping is an exceptional condition where if your polygon ends up against the edge of the screen, at least in some cases, you have to figure out exactly where that is and produce a new polygon that's been clipped by the edge of the screen. We try and avoid this because it's slow and it breaks the flow. Okay, but it has to happen. You also have, there are parameters that get sent along with vertices. I'll talk about those a bit in a second. They have to be clipped as well. There's a perspective division that has to happen to take place to get the effective perspective. Viewport transformation to scale the final results to the screen or to the window you're drawing into. And then finally, you have to assemble these vertices into something. Either a single one might be a point, 2 of them could define a line segment, 3 of them define triangles. We don't really go beyond 3, because if you go beyond 3, then you can just call them a bunch of triangles, okay, stuck together somehow. Okay, so now I guess I should have, no, this is a mistake. I should have lit up rasterizer here. This is the stage now where we take the geometry that's been produced and figure out what fragments it corresponds to. Okay, and this is done on modern hardware and in ATI's hardware in particular in a two-step process where we do a coarse rasterization first. We figure out which 8x8 blocks this triangle is in. Okay? And then once that's done, you figure out which 2x2 blocks within that, and within each 2x2 exactly which fragments are being touched. Okay? And that's done. That's done both to be sort of to be cache friendly, okay? Because we have these caches that are set up with this kind of blocking structure in them, and also so that we can reject whole piles of pixels at once or fragments at once that we know we're never going to hit the frame buffer. Okay, so you can work on a whole 8x8 block and go, we don't even have to look inside this one, right? Well, this one you do actually have to look inside. I don't have one here, you can't, but you can, one of these ones over here, you don't even have to look inside, right? And if you do, maybe you only have to look inside a quarter of it, okay? That saves work later, okay? So in addition to actually figuring out which pixels to light up, you have to figure out what parameters are associated with them, okay? You know their x and y coordinates, but there are other things put along with them like colors, texture coordinates for indexing into a texture, and in general, they're just parameters, and so you have to figure out what their values are, all right? And it turns out that the depth value, the depth value is just a linear combination, but to get the other ones, because you're in perspective, you have to do a divide at every pixel of a linear combination of two things, okay? That's just the way the math works out. So this is done using a plane equation to obtain these linear combinations here, and then a division of each pixel on the fragments, on the parameters for which it's necessary. And then, as I sort of referred to in the last time, there's some pre-testing that goes on that you can tell beforehand by looking, and by the frame buffer also has this hierarchical structure, and you can get a value back from there and decide once and for all that some large group of pixels, or even some particular pixel, isn't going to make it into the frame buffer because what's already there is already in front. Okay, so you don't even have to bother. All right, and this is done hierarchically again to save, really to save bandwidth down here, to save less stuff coming through here. Okay. All right, so here's a picture of a fragment processor, which I could have drawn for the vertex processor, but I didn't want to put up too many hardware-looking diagrams because the vertex one looks quite similar. What happens is fragments come in here, okay, and they can get written into one of these registers, of which there's 128 4 wide. Okay, 4 by 32 bit. That's why it's 128 by 128. All right. Then the ALU can operate on them. Okay, and it can read and write its own set of registers. And there's constants that are set by the host before the program gets executed. Okay, through some register interface. This is the control interface I talked about before. Okay, the ALU can operate on things. Then it can send stuff out through an output. It has 4 up to again. This is on current ATI hardware. There are 4 possible outputs, each 4 wide. Okay, and so you can send stuff to 4 different locations out in the frame buffer memory. Okay, there's a sequencer that controls this whole thing, and then there's this thing in green, which I've just drawn as texture. There's actually a lot in there. What happens is you can send out an address to the texture unit, and what comes back is some value read from your texture map. But there's a lot more can go on in there. There's filtering that happens automatically. Well, again, it's set up by the host, but happens automatically. It's a big deal what happens in that texture unit. Okay. But basically, the way the programmer sees this is kind of like this, where you have a 3-input ALU, and you can read stuff from registers, from texture, from constants, and you can write one of 4 outputs. Okay? And these are kind of the speeds we're at today, just based on clock rates and so forth. These not to be exceeded rates again. Okay, so one thing that's important about the way the fragment processors work is there's this notion of threading. So what happens on modern graphics hardware is when a fragment program hits a stall, you want to switch to something else that's ready to go. So for instance, if we look back on this thing, this texture, when I go out and fetch something that's in texture, it may not be in cache, and even if it is, actually, it takes a long time for it to come back, okay, as far as this thing's concerned. I mean, this thing's running at 650 megahertz. You got to wait for that data to come back. Well, you could just sit there and wait, but what happens instead is you don't. I mean, as the programmer, you don't notice this, but what happens is the hardware says, oh, this guy's blocked now. Let's switch to somebody else who's not blocked, all right? And so you switch to some other thread that's not blocked, and it continues on its way. And remember, you're processing, hundreds, thousands, millions of pixels, so there's always somebody who's ready to go, right? Or almost always. So to the programmer, it seems like a texture fetch only takes 1 cycle, when in fact it takes a lot longer. So you get this latency hiding effect. All right, that's not just to the programmer. It's to the program itself seems to take only that long. All right, except maybe at the very beginning and at the very end. right, when things are starting up. And it's important to understand, I mean, this isn't like sort of hyper-threading that you hear about on Intel processors or whatever. There's hundreds of threads, and they're very lightweight. I mean, it's possibly even thousands, okay? So the only trick is that you have to store the stalled fragments data someplace. And so what we do is, when you start your fragment program, remember, this thing's got up to 128 of these four-way registers, right? When you start your fragment program, you say how many registers you use. And if you use all 128, well, it doesn't leave you much storage for other fragments data, okay? Turns out there's actually backup storage beyond 128, but just forget about that for a second. But if you use like only 4 registers, well, and you do 128 divided by 4, you know, that's how you could do that many threads, plus, you know, multiplied by the extra factor. So the fewer registers you use, the more threads you have, therefore the greater latency hiding that's available. Okay. So finally, we'll get to the per pixel operations in the frame buffer. The stuff that goes on here is the application of fog. So you can have a fog color that, you're trying to simulate being in a foggy atmosphere or something. Things very far away are just going to look white. Things closer up are going to look less so. You can just do this linear blend to get that effect. With the fog factor, there are these tests. The depth test is for doing hidden surface removal to find out what's closest to you. And there are these other tests that are used to do various rendering tricks to do things from everything from shadows to polygons that look like trees but are actually just polygons. There's all kinds of stuff you can do with these tests. Then there's also this notion of blending the incoming color with the color that's already there. So if you have something that's translucent, you want to take some of the translucent color and some of the color that's already in the frame buffer and blend those together. And the important thing here is we have this 32-bit floating point frame buffer that you can use. You don't have to use it. There are also fixed point formats, but it can be useful. And let's see, I think, so I've got a couple pictures here, and I'll show a little demo in a second. What can you do with all this stuff? Well, you can make these nice pictures, and of course, they never look as good on a projector as they look on the screen, but you kind of get the idea. I mean, this is pretty complicated scene with pretty soft-looking stuff, and this is one frame, that's rendered at 30 or 60 frames a second. Right? And so why would you want the 32-bit frame buffer? Well, here's, again, it's a little hard to see maybe on this projected like this, but you can do this high dynamic range stuff where you draw things, right? If you only have 8 bits, you don't have very much dynamic range for your lights. But if you're able to draw things with a lot of dynamic range, you can draw things into the frame buffer that are really, really bright and things that are really, really dark in the same picture. And then when it comes time to actually display it, it's like setting the aperture on your camera, and you decide, well, are the really, really bright things going to get, are the dark things going to get brighter, and so the really bright things are going to get completely overexposed, or vice versa, right? So you can decide how to do that. But if you didn't have the high dynamic range frame buffer, you couldn't do the first step, which means you couldn't draw pictures like this, okay? We can also, and again, we can do this anti-aliasing, which means essentially, well, there's different ways to do anti-aliasing, but it's to avoid these jagged artifacts along edges. One way to do it is to use a lot more screen area than you've actually got, and then you just shrink the whole thing down. That's maybe the obvious way. But there are other ways as well, and again, because we have all this memory bandwidth and all this computational power, we're able to do that. It makes things look a lot better, and you don't see these little jumpy, crawly things. Okay, so let me take a minute, because every graphics thing we have to have I got to have a demo. Oops. So this takes a second to start up. This was developed by our developer relations group, just to kind of show off the sorts of things you can do with this level of graphics hardware. I guess the thing to remember about it is that, in the beginning especially, it's all being rendered at 30 to 60 frames a second. Okay, it's not a movie what you're watching. And we'll just hopefully let it do its thing. It's almost ready here. And I guess, I didn't plug in the sound. Oh, I'm not going to do that now. So here we've got this effect of rain and lightning and puddles, right? With moving ripples. And again, it's this is I'm moving the mouse now, right? And I can do stuff with it. And again, all this stuff here, you can, maybe when we get a little further along, I'll show that, you see all this complicated stuff here. Most of it's just a few polygons, and it's all done with texture mapping. And again, texture mapping isn't just for putting images on things. You can also just use texture mapping as a sort of filtered lookup table. So you can use any kind of data you want in the texture map, including lighting data, bump data for how bumpy walls are supposed to be, all kinds of other stuff, anything that you might want to have per fragment. Okay, and so there's there's a bunch of fancy stuff going on. These cobblestones, the cracks between them are modeled with a very simple kind of ray tracing technique that's possible, that's tractable enough to do every fragment. Let's see, I think, yeah, the streaks running down the window here, those aren't run by the CPU at all. There's a little algorithm that runs on the GPU that moves a little water droplet down every frame, or figures out how much to move it down, and randomly perturbs it back and forth to get these little streaks. Okay. There's other similar stuff going. The curves that the wires, these catenary curves in the wires here, those are also calculated on the GPU, not on the CPU. All right. I'm getting to the other part of my talk. So, okay. So I guess that kind of, hopefully that gives some idea. And again, this is all, happening at 30, 60 frames a second. Okay, so I think that's enough of that. Okay. Okay, so now I'm going to switch gears and talk about graphics programming interfaces, or APIs. All right. So I told you about all this great hardware, which I'm sure a lot of you already know all about. How do you get to this stuff? Okay. So, what do programming interfaces, graphics programmers have to do? They have to provide a software interface to graphics hardware. All right. That's kind of what I just said. At the lowest level, what you'd like to be able to do is expose all the functionality of the hardware at full performance. Okay. But on the other hand, you'd like to hide some device-specific details, and you'd like to limit the interface changes from generation to generation of the hardware. Okay, and clearly this first bullet point and the second two are almost always in conflict, and so you've got to kind of figure out where the balance is. All right. At the higher levels, you want to simplify application programming, all right, which I treat as somewhat, it's not providing a software interface to graphics hardware at the most basic level anymore. It's making it easier for the application programmer to write applications. Okay, and so the large classes of these things are scene graph libraries and shading languages, which are kind of completely different things. I'm not going to talk, scene graphs libraries were a big deal a few years ago. I'm not going to talk about them at all. These days, there's a lot more interest in shading languages. Okay. So the low-level interface, sort of historically, what happened was there was this fixed function pipeline. I mean, that's the way the hardware was the vertex processor did certain fixed things, right? The rasterizer, well, still does fixed things. The fragment processors did fixed things. All right, we didn't even really have notions of processors. They were just these were just stages in a pipeline. All right. And so OpenGL and Direct3D kind of took two different approaches to this. OpenGL required all the functionality that was in this pipeline. It was fairly had a lot of features, and you had to go through a software path if you didn't have the features somehow. Okay. Direct3D took a different approach, which was to use these capability bits, which would say which things were in there and which weren't. With DirectX 10, this has all become a lot more stringent. So DX10 has sort of almost gone the path now where you better have all functionality, and you better not do it in software either. Okay. Both of these provide sort of a vertex and fragment program, they eventually did provide a vertex and fragment program assembly language kind of thing. I put it in quotes because, except for maybe one brief moment in time, that assembly language corresponded to no actual hardware. So to me, an assembly language is the ASCII equivalent of a machine language. There was no equivalent machine language, so it can't be an assembly language. But it looks like an assembly language. DirectX 10 has even gotten rid of that. Okay, so you can't in DirectX 10 you've got to program with one of these higher level languages. Okay, so let's talk about these some of these higher level languages. Sort of the grandfather or something, grandparent of them was this thing, RenderMan, which was used and is still in heavy use in the animation industry. It was designed to do shading. It was designed quite some time before programmable graphics processors were even a twinkle in someone's eye. I think this was done as a software thing for doing animation rendering, and it wasn't designed for hardware. It wasn't intended for it. I mean, but RenderMan's actually a great model. I mean, it was Pat Henrihan knew what he was doing. So then there are these other languages that have come out to be sort of more hardware, more amenable to hardware, I guess is the reason for them. There's the high-level shading language, HLSL, which comes with DirectX from Microsoft, GLSL, GL shading language, OpenGL, and then there's a sort of thing, somewhat higher-level thing called CG. It was supposed to be, the idea was C for graphics from NVIDIA, okay, which runs on both DirectX and OpenGL. These all provide C-like languages. They're reasonably general in the computation they admit, but they expose some hardware. They're sort of tied to the hardware in some ways, like they call out specially 3- and 4-element vectors as one example. GLSL is the only one that supposedly virtualizes the number of passes. If your program's too long, it's too complicated for it to run in one pass, then GLSL will cut your program for you and run it in more than one pass. As a practical matter, this hasn't really come to fruition. It's not so easy, first of all, and it just hasn't really taken off. And these are sort of becoming, or have been becoming, the only real means to get at the programmability. Okay, the actual vertex and fragment processor instruction set is just not exposed. The hardware companies, including mine, don't tell you what that is. Okay, so the only way you can get at it is by using one of these higher level languages. All right, and contrast that to the CPU world, right, where the CPU instruction set is published. Okay, and you can write in that if you want to. You can't here. Okay. So I guess my idea about this from some time ago, and I guess this picture reflects it was some time ago, because I don't have all the lines on here that now exist, is to sort of look again at what the hardware abstraction is. All right. So OpenGL originally was not programmable. It wasn't meant to be. And graphics memory wasn't accessible, really. It wasn't directly accessible. In fact, you had different kinds of graphics memory for the frame buffer, for texture memory, for storing vertices if you had such memory. But now it's all the same memory. Okay, and it's sort of special purpose, not directly accessible. So the changes have been that now we have programmability, and we have this kind of flexible use of graphics memory where one time, the first time through your graphics memory is the frame buffer. The second time through, it's a texture. You use a texture to do your next pass, and so on. You draw something in your first pass that you use as a texture in your second pass to draw the second one. Okay, so if I do that, then I sort of come up with this idea for a new low-level interface, which recognizes that these stages in the pipeline over here are all programmable. Now where I put programmable here is maybe stretching it a bit. Certainly the vertex processor is the command processor. I've called that programmable in the sense that you can, it's not like you write programs for it, but you can decide, you can tell it what form its data is supposed to be in, and it's very, very flexible. So you can essentially program it to say how it's supposed to fetch its data, okay, or what the format is. And so the idea is, I want to distinguish two things here. We've got a data path, all right, and so it's the routing of the data, and then we have these parallel data processors, all right, and we have some fixed function stuff that's always going to happen as well. So once we expose programmability, I don't know why we need fixed function anymore. Okay, so all the stuff that was in OpenGL, like to set transformation matrices and to do transformations, or to set a particular function to use when you're doing texture mapping, all these things. Why do you need that anymore? Why have that since you can write a program? And that's what our drivers do anyway. When you ask for that kind of stuff, they just stick a program in that does what you ask for. So why not let the application do that too? All right. And then I guess the idea is, well, okay, let's just go ahead and expose the machine language. If you don't like programming in a machine language, well, don't. Use some higher level language, just like you do on a CPU. Most people don't program in x86 anymore. Use a C compiler, fine. But if you need to use x86, or you need to find out where your program's going slow, it might come in handy, okay? And then you use libraries to implement the fixed function stuff. And what you really want to expose is the memory capabilities and the routing, and at least to this kind of stripped down interface. One other thing I should say here, right, I've drawn this line here because sort of above this line is the world of geometry and sort of streaming data. where vertices are coming through, and one vertex comes through, and then about the back, some other vertex comes through. Or, and now I've drawn this, put in this primitive processor here because DirectX 10 allows you to not only process vertices, but to process the primitives that get put together from those vertices. Okay, so we've got sort of this streaming thing above here, and then below this, the rasterizer just blows up these bits of geometry into fragments, okay, that you can think of as just as running these parallel computations. All right, each fragment is running in parallel with a bunch of other fragments. So now, in this world here, this is much more the sort of data parallel world. Up here, we're kind of streaming. Here, we're data parallel, okay? And that's why I drew this line here. Okay. So this kind of fits with these new GPU applications. You can see where I'm leading to, probably. So we have these recent applications that up until recently have been mostly the purview of academics, where people have been very interested in using the power of these graphics processors to do other things other than graphics. Okay, and if you want to do that, it kind of makes more sense to talk about this thing as a processor rather than as a graphics pipeline with graphic state that needs to be set. Okay, so these are kind of some of the kinds of things that people are doing, and that even includes some new graphics applications, right? Where this pipeline that I've shown, it's good for doing a particular kind of graphics, Z-buffered rendering, Z-buffered hidden surface removal with texture mapping, I suppose, right? Ray tracing is quite a different deal. Yet now people are trying to do ray tracing on these same processors, all right? Even though that's not what they were built to do. Okay, it's just a sort of a recap of the compute performance. I've already talked about most of this stuff. Okay, 240 gigaflops, a quarter of a teraflop is not to be sneezed at, I guess, at least if you can really get it. And the memory bandwidth is kind of the same thing, and also very high, much higher than most CPUs are going to give you. We have this, low latency for getting 4 floats out of a cache. And here I'm just talking about the fragment processors. Okay, this isn't even the rest of the chip, right? Okay, and then we have, we can transfer data quite quickly to and from the GPU memory. Okay, so now I come to ATI's what we call CTM, okay, which is our new interface for computation. So yeah, right, CTM stands for close to the metal. What we do is we expose the fragment processors, and we try to stop using graphics terminology, but you'll see here I haven't completely weaned myself of it, and sometimes it's easier for people to hear the graphics terminology, and if I say the computing one, they're like, what are you talking about? And I say texture. Oh, now I understand. So there'll be a little mix-up of that. But anyway, the idea is to expose these data parallel processors, just the fragment processors, okay? We don't worry about the rest of the pipe yet, and memory, all right? And so we specify the actual processor instruction set. You can open up the manual and find out what instructions the processor actually runs, and you can program it in machine language or assembly language if you want, all right? Because there's an ABI, application binary interface as well, for loading programs into it, all right? And it leaves memory management entirely up to the application. See, in the graphics APIs, right, you don't really talk about memory. You talk about, well, I want to load a texture now, or I want to set up this frame buffer. And the driver somehow decides behind the scenes how that corresponds to memory. We don't do that. We say, here's memory. Do with it as you will. Again, much more like a CPU. Okay? So an important thing is that it does have this device-dependent component. That's the instruction set architecture, right? That is going to change, or there is certainly the likelihood that it will change with new GPU incarnations. Okay, but there's this control hardware around it that doesn't have to change. Okay, so there's this stuff about how setting up the memory and setting up the program that can be abstracted and can be device independent. Okay, so we provide a model of the GPU command processor. I'll show you a picture in just a second. We try to hide details about the graphics pipeline that aren't interesting to people who are doing computational programming. Okay, but you still need to have them set right or things won't work. And again, this control stuff is architecture independent. So we're focusing on computation, and as a result, we don't export the whole GPU. In fact, we don't even export the whole GPU right around the areas that we are exposing. So for instance, right now, we don't expose texture filtering, even though that wouldn't be difficult. And we don't expose vertex programs and a number of other things. Okay, we do support multiple GPUs in the same system. So here's a block diagram. What happens is the application talks to CTM. I mean, you can think of CTM as sort of as a third graphics driver. We've got OpenGL, we've got DirectX, and now you can think of CTM as being another way to get at the hardware. Okay, so the model for it is the application talks to CTM through a very tiny interface with only 4 calls in it. You can open a connection to a device. You can close a connection to a device. You can submit a command buffer to the device, and you can find out if that command buffer has been consumed or not. Okay, so what this exposes is that there is in fact a command processor. Okay, inside, or what. I mean, it exposes what it abstracts. Anyway, there is a command processor that you send commands to, and I'll show you what the classes of commands are in the next slide. And then that thing is connected up to a bunch of memory, both memory on the host, PCI Express memory, and memory on the GPU. Okay? And inside that memory are things like maybe you can pull commands from inside this memory, I mean, through this memory controller instead of sending, well, that is actually, I'm sorry, that is the way they get pulled through. Okay, this thing just has these 4 commands, I mean, these 4 API points. Instructions for your fragment programs are in here. Okay, constants, inputs now, those are textures, outputs, those are frame buffers. Okay, so these are just memory. Now, and I want to make clear here that there's in a way, there's 2 things going on. There's commands that come into the command processor and send control through this thing, control around this thing, and that also tells the programs when to start. The programs that this thing runs are not these commands. They are these instructions over here. Okay? So examples of, let's see, no, I guess I didn't put in the commands, which is too bad. But okay, so some examples of commands would be things like start program, okay? Or set input address to something, okay? Or set constant 57 to, 3, 4, 5, 6, 7, something like that, okay? Those would be examples of commands. And then instructions are things like multiply, add, sine, cosine, stuff like that, okay, that get run by the actual program. All right. So now how do we generate code for this thing? These are the instructions over here, okay? So we leave that up to the app. Unlike the graphics drivers, we leave that up to the application, okay? So you could write your own compiler if you want. You could write directly to assembly or machine language if you want. But we provide some tools. And we have a source code for a sort of non-optimizing compiler. Then also, ATI has an optimizing compiler that accepts a sort of intermediate level language that we can also give you if you want optimized code as well. The only thing about that's opaque though, because it contains some real intellectual property. Okay. So that's how you can actually program this thing at any level you want. We're trying to encourage people actually outside of ATI to do compilers and other kinds of things that you'll need to do this kind of programming, like debuggers, profilers, things like that. Okay. So let me sort of contrast CTM with some of the graphics APIs. Some of the problems with graphics APIs are that the application has to manage this graphics state, which typically the application doesn't care about. Plus, it can be complicated to do right. The code generation is by design hidden, okay, which is fine, I guess, if you don't care. But if you're trying to really find out why your program's going slow and why did you do this in the first place, you wouldn't even bother if it wasn't for the performance you get. So if you're trying to find why your program's running slow, it's a little bit hard to do if all you have is a high-level language and a slow program. Okay. The memory format and management, they're hidden in the graphics APIs. We don't hide those, again, because we figure, well, the application knows what it wants to do with the memory. We don't want you as an application writer probably don't want the graphics API deciding, oh, this should be in host memory now. I'll copy it out of GPU memory and stick it on host memory, or vice versa. These things can go on without you even really knowing, except that they affect your performance. And all of a sudden, why is it so slow at this point? So we don't do any of that. We leave that to you. And another problem, and this has actually happened too, is that at ATI, of course, we're really concerned with how well games run on our machine, right? And so somebody's writing some GPU application at Stanford or wherever, and they write up something, and then they get a new driver release, and they go, great, a new driver release, maybe that'll fix my bug. They download it, and all of a sudden their program that was running so great before, except for maybe a little problem, runs twice as slow. Why? Because we put in some optimization that was super important to make Doom 3 go fast, okay? But destroyed this poor person's application, okay? And And so we get rid of that by making the compiler sort of not part of the driver anymore. Once you compile your code, you can be sure it's not going to change. Okay. So, and you know, and it goes on and on. APIs are mediated by the Windows system, and you have to worry about all that stuff in the driver, and that can affect your performance. Where you don't even care about what's showing up on the window if you're writing one of these things. So why should it matter? All right, and you don't want to have your application coupled to display policy if you're not using the display. Okay. And so, I mean, this is, you know, performance and functionality. You may have, you don't have predictable performance and functionality, and it's a problem for some people, or a lot of people. Okay. So I think I went through most of this, except maybe the command buffer packing and submission. Yeah, I think. Right, so you also have the ability to pack your own command buffers instead of the driver doing that for you. And so you decide when your program starts. You decide when the right time is to invalidate caches or things like that, okay, rather than some driver thinking it knows what you're doing because it thinks you're doing graphics, deciding that for you. So and I think the big point for me about this is that graphics APIs, they abstract the graphics pipeline, a particular one. Okay? CTM, we try and extract the actual processor or a piece of the processor. Okay, so here's some sort of examples of, these are speedups we've gotten by programming in CTM instead of programming in OpenGL. All right, so on matrix multiply, we get a factor of 4 speedup. And these are because we can access, we can get to features that are either inaccessible or not, or managed in a way that doesn't allow us full use of them in the drivers, okay? So we're able, on matrix multiply, we're able to get a huge speedup. I mean, we're running it at 110 gigaflops or something, which is pretty fast. I mean, that's a lot faster than most CPUs. Yeah.
The matrix multiply. It seems like the objective of the whole pipeline is to process the pattern in frame buffer. Now, what I'd like to know is, the matrix multiply, are you passing both matrices to be multiplied into this pipeline and getting an answer in the frame buffer, or can you multiply passing one matrix with the other matrix being in the frame buffer? The related question is, can you be writing into the frame buffer, and then can you get data out of the frame buffer back into the host at the same rate as you write it, in order to do both at the same time?
Okay, let's see if I got all that.
So the first one
yes.
was both matrices passing.
Right. So
the second one is, could one of them not be?
So this one's easy. The matrices are in memory, okay? So they don't come down through that pipeline chain. So the matrices are either in PCI Express memory, which is on the host, or in GPU memory. Okay, so there's not really a notion of a frame buffer or passing something in. They're just in memory. Yeah.
Okay, so the preferred, so both matrices were in the memory?
Are in memory, yes. And so the 110 gigaflop number, that's for both matrices in GPU memory. If they're in CPU memory, then you got to go through PCI Express transaction to get every element out.
Matrix multiply both matrices some
on the graphics card.
Not to exceed M.
That's correct. Yes, right. That's right. And that's right. This is for the that's why I probably should have kept my mouth shut about the numbers. That's why this slide doesn't show numbers. The point of this slide is showing why you'd want to use CTM instead of OpenGL. Okay, but I'm sorry. So, but I don't want to stop your question.
Just get to the last part.
Yes.
The last part about being able to move data at high rates from the M back to the host.
That's right.
You're also driving at a similar speed, hopefully, to the M.
That's right. And today, actually, CTM does not expose the ability to do a DMA at the same time computation is going on, even though the chip can do that. Then that's something where it's almost at the top of our list at this point. So that would allow you to do that. But today, no. Today, it's got to be serialized, essentially. But there's no reason why you shouldn't be able to do that. Anyway, and so these, I won't, you guys get the idea. These are this GPU ray thing. This is a ray tracer that was done at Stanford, a simple ray tracer, and then this QJulia is a Julia set rendering done by one of our people. Okay, and again, we get these speedups by being able to get a hold of features directly that we can't through the graphics APIs. Okay. Okay, I'm almost done here. I feel like I need to, probably some of you have heard about it. NVIDIA also has an initiative for, they've also got their new generation of hardware is also out. Ours is not yet. They have an initiative for doing GPU programming as well for people who want to do computation and not graphics. I guess I'm violating a rule here. I'm probably not supposed to talk about my competitor's product or something, but So I'm not going to say much about it. If people have more specific questions, feel free to ask me afterwards. But it really is specifically for GPU computation. It, too, is sort of like you got OpenGL, you got DirectX, you got CUDA. The programming model is they give you a slightly augmented version of C, which is augmented enough so you can express some stuff about threading. And that seems very attractive. But they do not expose the actual processor ISA or the sort of command processing nature of the way the thing works. It's a much higher level. I say much higher level. It is a higher level abstraction than what we're providing. That doesn't tell you as much about the underlying hardware. I'm biting my tongue not to make a bunch of judgments on that. But if you want to ask me, go ahead. Otherwise, that's what I won't say anything more. Someone from NVIDIA to tell you more about this. Okay. So I'll finish up. I guess the conclusion of all this is, that good image quality requires a lot of computation. And gosh, well, these GPUs have a lot of computational power, and you can actually use them to do things, to compute stuff that might not be graphics stuff, okay? And it's not just, of course, the number of gigaflops. It's also this very high memory bandwidth. Graphics APIs aren't always a good fit to expose the computational power, particularly for non-graphics things. Real-time graphics has changed, and it's going to continue to change, all right? So the big changes have been sort of this programmability in single memory. But I think the changes that are starting to come more is that the line between computation and graphics and blurring, is blurring. I showed you in that toy shop thing. Some of the stuff it was doing was pure, sort of in a sense, pure computation, but the result was graphical, right? So you're doing some simulation to find out how water runs down a piece of glass, all right? So what's graphical and what's not starts to become not quite so clear. And people are doing things like game physics on GPUs, ray tracing on GPUs, which is sort of the opposite way around, where you are doing, like I said before, you're doing graphics, but not in the way it was intended. And we're going to see, I think, the use of the CPU and GPU in a much more finer grain use than we have in the past. Again, some of you may have heard that AMD has announced we're going to put a GPU and a CPU on the same die by, I think, the end of 2008. So you're going to start, my opinion is that you'll start seeing a much tighter coupling, and that'll lead to doing some things in a new way, not only for computation, but for graphics as well. So that's what I had, and I'll take some questions. Why don't you start with you?
Excuse me, Mark.
Yes.
I said at the beginning of the talk that this talk is going to go on to Google Video, so any comments or questions
Thank you. Okay. Over here.
There's a classic paradigm, which is the wheel of reincarnation of graphics technology,
right, where
first you have dumb frame buffers, then you put a little processing, and then you get these massive processors, and then it all gets sucked back into the CPU again. How many times has this gone around? Do you think it's still turning?
How many times has it gone around? I'm not sure how many times it's gone around. Do I think it's still turning? Yeah. Will it ever stop? Probably not. I think there's some stuff that characterize it. I mean, there's still some things that are very different about GPUs and CPUs, and some of those things, if you want to continue to do graphics well, can't really change. You have to have some way to do a lot more computation than you can on a CPU, and the way we've done that is through this parallelism, right? And you have to have a way to get a lot of memory bandwidth. So that stuff's not really going. I guess. I mean, so if you could do that on a CPU, then fine. But today you can't really. And even you start to see moves towards multi-core and so forth, and they start to go down that road. But there's still a ways to go before they would actually become GPUs. Again, my opinion. There's also this idea of the rasterizer, which I think is really sort of architecturally what distinguishes GPUs from CPUs. And as long as Z-buffered graphics is, I don't know, a preeminent way of doing graphics, I don't see that going away either. It's possible we might, all decide it's time to do ray tracing. We're done with this Z-buffered rendering junk. But until that happens.
It may be that the next, as you say, 2008, when AMD puts GPUs into their CPUs, we've completed the turn, and we're back to effectively dumb frame buffer and a very powerful CPU.
Oh, I see. Yes, that's right. Yeah. No, I mean, yeah. I mean, if you it's true. If you divorce the, if you look at a GPU as a long processing pipeline, and then there's a little bit of thing at the end that does video, right? And you just take off you cut off the video thing. Now you've just got a big, powerful processor that's got this weird architecture. So yeah, I mean, you're right. You stick that on the same die as a CPU. Well, now you've just got a heterogeneous processor, and that's all it is. Yeah. I don't know what to say about that. Yeah. Well, now I guess we'll
try one that's
yeah.
safe.
Okay.
So if you're going to combine these two things on one chip, the graphics processor needs a lot of pins for this huge memory bandwidth today. So assuming what gets combined together on the same chip is something high-end, or at least high-end as of today, middle end, 2008. Where do you get the pins for you're going to try to share the memory band? I mean, how does this all pan out? Right now you've got this separate memory for the GPU. And it seems like a real shame that you just don't also improve the CPU's access to memory band. Something else that we have to care about here.
Right. And I can't, I can't, these are, all I've said is what's been announced. I can't, not that I know tons anyway, but I can't say anything more than that about what, details about how it's all going to work. You can think, but maybe the thing to think about is integrated parts, right, and how those work. I think that's probably the better analogy than some high-end thing in the beginning. But I don't know, frankly. I think we'll have to see where it comes out. Yeah, go ahead back here.
So in the late 90s, at the consumer level, performance was driven by games like Quake, Doom, and such. But recently, I understand that desktop windowing systems such as on Macintosh and Vista are starting to use GPU capabilities for rendering. Is it likely that those sorts of applications are going to drive technology at any point more so than gaming technology?
I guess my opinion is not really, because while it's true that Vista's, for instance, is going to uses a lot more graphics processing than anything Microsoft has put out before, it's still not very much compared to games or even mid-level games, and it can't be that much, frankly, because they have to be able to go out on not very powerful graphics processors. So I don't really think so. Now, I shouldn't. I could imagine there might be some whizzy desktop feature that becomes very exciting that will drive something. But generally, it's hard for me to see that. Let me give somebody else a chance. Yeah, why don't you? Yeah, go ahead.
I'm just wondering what you have to say about DX10 having an impact on the CTM with regards to the unified shader model, and what sort of threading concurrency type constructs are exposed within CTM for cross-thread communication and things like that.
Okay, so I didn't hear the very beginning of the first
just
question.
The unified shadering model,
yes.
That has an impact with regards to using vertex processing units within CTM,
right,
and geometry shading units as well.
Right. Okay. So as some of you obviously know, DirectX 10 doesn't mandate this, but we've certainly seen there's been a trend to combine the vertex processor, the primitive processor, and the fragment processor in the same hardware. Okay. Logically, they still are separated in this pipeline, but the actual hardware that's used to run each of those is the same. So the question is, does that allow for what effect does that have on, say, vertex processing for CTM? The answer is it doesn't really have much, except that now you get to use, now you have even more power available to you because you can use all the processors to do your processing instead of just the.
So that doesn't expose extra features that are only available in a geometry shading unit or a graphics shading unit?
Well, no, because if it's the same hardware, like if you look at Xbox 360, it's the same hardware. We would just expose the instruction set architecture of that machine. You do what you want. Now, again, in CTM as it exists today, we don't expose this rasterizer for. Come up afterwards if you want to know why we didn't decide to do that in the beginning. Until we do that, we can't expose all the power of the machine. Okay, so then there was another question about threading.
Just sort of what sort of communication mechanisms are present for cross-thread communication and synchronization within CTM?
Right. Now, so again, maybe you're familiar with NVIDIA's new hardware, yeah. So he's asking about what kind of inter-thread communication there is. Now, right, remember, I said these things, right, there's 16 of them, and they're all running in parallel and all this stuff. Can they talk to each other? No. Okay? And that's just, our current hardware doesn't say it doesn't allow it. It turns out that we do have someone who's figured out some wacky backdoor that we couldn't expose to the public that, that does allow you to do it in some strange way. But it wasn't designed for that. I can't talk about upcoming products, but it's true that NVIDIA does have a product that allows some form of inter-thread communication with shared memory. Yeah.
With the standard pipeline, you can never read back from the frame buffer into fragment shader. So does that have an implication on the things you can do with CTM? Because essentially you can't say, what's my current result, and then modify that result.
The standard pipeline is a pipe, that restriction of not being able to read from the frame buffer in a fragment program is really it's one imposed by the drivers. I mean, there's nothing wrong with you, and you can do this in CTM, to set your frame buffer address and your text address to be the same thing and write to the same area of memory you're reading. You might not do what you want because there are these caches in the way that are going to act strange, and unless you're being careful how you use them or you're careful to use uncached reads and writes, strange things will happen. But that doesn't even go. I mean, you don't even think about things that way in CTM. Yeah.
What about sharing the graphics resources between different applications running at the same time? Or, well, by Windows Vista interface, some other application?
So the question is about sharing resources. Okay, so for graphics drivers, right, the way DirectX has had sort of an exclusive. You run one DirectX application, that's it. Or at least D3D application. OpenGL has had taken a different approach where you can have multiple ones. None of that changes here. The way CTM works is when you make that initial call to open this managed connection, you can say how much memory you want of these different kinds, and it will try and give you that when you come back. If you ask for all the memory you could possibly lay your hands on, there's not going to be anything left for anybody else, so you're not being a very good team player. But there's nothing, I mean, right now there's no virtualization of those resources, right? Because we don't want memory copies going on behind people's back. Am I answering your question? I'm not sure if I am.
But there is possibility running in parallel some applications, assuming not all memory.
Yes. Well, that's right. So you can do that, right? So you can have, say, you could have a couple OpenGL applications running in there, taking up some memory. Then your CTM application comes along and says, "Oh, I need 30 megabytes or something." It goes, "Okay, you can have 30 megabytes. That's not being used right now." And then you can go ahead and do that. And of course, you're not, you're really being time sliced, just like you are on a CPU, except you're actually holding these pieces of memory. Right, so there's nothing stopping you from doing that. And there's nothing, I mean, the way OpenGL works today is all that stuff's managed for you underneath. All right, so if you forget about CTM, you can run multiple OpenGL clients, and if there isn't enough memory on the card, it'll copy stuff back to the host or keep shadows of it on the host, pull it back in when it needs to, like a virtual memory system. So you can imagine doing that as well. And Vista actually has some support for doing that for graphics, virtual memory. So I think I've answered probably too much, but Jim, why don't you?
Yeah, it's much easier to get peak performance with a small application kernel than with a full application.
No doubt about that, yes.
So has this stuff been used on something that's
sizable,
substantial, like a weather simulation or something like that?
Yeah, it's starting to be. There's a company called Peakstream, which is right around here, a startup company, and they have some customers. Most of them, I believe, some are financial and some are doing seismic stuff for oil and gas, and they've had some success, definitely. But you're right, as with anything, when I just put up these little things, they're also kind of not to be exceeded number, and the real issues are not how many gigaflops the thing has, but whether you can really use all the memory bandwidth and how fast it takes to upload and download things and how big a computation you can run before you have to read stuff back. So you're right, and so yeah, there's starting to be some successes there, but there's a lot more to do. Yeah. One more question.
You said that it's almost IEEE.
Yeah.
Can you tell us what the differences is? And as you go forward, moving more towards general purpose uses, is there any drive to make it more standard, to add double precision, that sort of thing?
Yeah. So the question is about IEEE, and I let slip the comment that we're not perfectly IEEE. We don't have different rounding modes, so we do round to nearest even. We treat denorms as 0, okay? and they will turn into 0 except in certain pass-through operations. That's it. There's a mode in which we don't treat NANDs correctly, but that's for some graphics, and you can turn that off. That's it. Otherwise, we're IEEE, except there's no signaling NANDs, because these things don't have interrupts. And again, for some applications, that's an issue. But now, right, and no double precision today, but there's definitely, I think NVIDIA's already announced they're going to do double precision sometime within a year, or some upcoming part's going to have it. I think that we're probably going to move that way as well. So yes, we're moving that way. The denorm support, I don't know when that's going to happen. Signaling NANDs, that's a ways off, because that requires these things to be interruptible, which they're not.
Well, let's thank Mark for his time.
Thank you.